Everyone, welcome to CSE Core Concepts in my series of data structures. In my last video, I had discussed about the binary tree traversals and binary search trees. So here in this video, I am going to discuss about a type of a binary tree which is called as AVL tree. Precisely telling, this is a type of a binary search tree. If you have any questions regarding binary tree and binary search tree, you can go through the video where there it is understood that binary search trees are a type of binary trees. Now here AVL trees are also a type of binary search trees. So of course they are also binary trees. So any tree which is a binary tree means what? That it can have maximum 0, 1 or 2 nodes. So this AVL is named after 3 scientists who discovered this, and these type of trees are basically helpful for balancing skewed trees. So what are skewed trees? I have discussed it in the introduction lecture of video of these trees, where this type of a tree, if the nodes are formed only in the left direction, they are called as left skewed trees, and if the nodes are formed only in the right direction, they are called as the right skewed trees. In this case, how to balance a skewed tree? For that we have to find out the balancing property. Now what is the balancing property? The balancing property in case of AVL trees says that the height of the left and right subtree can differ by at most 1. That means there can be only a difference of 1 node between the left and the right subtree. So balance factor of the node can have either value 1, that is positive, minus 1 means one subtree is 1 less than the other one, or they can have 0. 0 means both the trees have equal amount of nodes, equal height. Okay. So the formula for finding out the balance factor is that height of left subtree minus height of right subtree. So let us consider this binary tree. You can see here this tree looks very unequal because on the left hand side, what is the height of the tree? You can see from 33, 13, 11, 8 and 9. Okay. So the levels are more. That is 4 is the height of the left tree and left side. And on the right subtree the height is only 2. More regarding the height and depth you can go to my previous video and you can understand. So let us compute the balancing factor of the root node. So height of left subtree is what? 4, because 13, 11, 8 and 9. Okay, 4 levels are there. So 4 minus height of right subtree is what? 2, 53 and 61. So it is 2. So the balancing factor should only be between 1 minus 1 or 0. So of course this indicates that this tree is an imbalanced tree and we have to balance this tree. Next, let us compute the balancing factor of the next left subtree. So it is height of the height of node 13 is what? 3 on the left hand side minus 1 on the right hand side. So 2. Again it is an imbalanced tree. For 11 it is the left subtree is height is 2. There is no node on the right hand side. So it is 0. So 2 minus 0 is 2. For 8 it is no subtree on the left hand side 0, 1 subtree on the right hand side, that is 1. So 0 minus 1 minus 1. So 8 to 9 is the only balanced subtree in this binary tree. Now for the last node, no left and right, so the balancing factor is 0. Now for 21, no left and right, again the balancing factor is 0. Now let us come to the right subtree. So for 53 there is no left subtree, so 0 minus only height of the right subtree is 1, so minus 1. So it is a balanced. 61 it will be 0. So now let us see how to handle the cases when we have skewed trees. First we will discuss about the right skewed trees. They are also called as RR because right skewed rotation. So consider this right skew. You can see 11, 12, 13 they are coming on the right hand side. Now in this case, first of all you have to compute the balancing factor of each node to find the critical node. Critical node refers to the node which for whose balance factor is more than is other than 1, that is critical node. So here in case you can see for 11, the left subtree height is 0, right subtree height is 2, so the balancing factor is -2. So it is critical. So for 12 it is no left but only one right, -1, and 13 is 0. So here the critical node is the 11th node. So whichever is the critical node, the next node becomes your rotation node. So you have to perform an anti-clockwise rotation from the rotational node in such a way that this is what is formed. So you have to just move, turn, you have to keep the rotation node fixed, and you have to turn as if you are turning a compass, right? So this way if you do, 12 becomes your root node. On the left hand side is 11 and on the right hand side is 13. So if you compute the balancing factor of all the three nodes, like 12 it is 0, 11 it is 0, and 13 is 0. So it is in the range that is of -1, 1 and 0. So of course this tree has now become a balanced tree from a right skewed trees. Similarly, you may have left skewed trees, which is LL rotation. So you can see here 11, 10 and 9. This is a left skewed tree. So here in this case again first we are going to compute the balancing factor of each of them. So for 11 it is 2. So that is what? It is a critical node. 10 it is 1, and for 9 it is 0. So who becomes our critical node here? 11 becomes the critical node and 10 is the rotation node. So you have to keep the rotation node fixed and rotate in a clockwise direction this time. So if you do that, so who becomes your root node? 10 becomes your root node, and 9 is the left subtree and 11 is the right subtree. In each of these cases, one thing you can observe that they all can follow the condition, satisfy the condition of a binary search tree. So if you remember what is a binary search tree, that the left nodes are always smaller than the root node and the right nodes are always greater than the root node. So they also follow the binary search tree. That is why AVL trees are a type of binary search trees. Now if I compute the balancing factor of all three nodes, they are coming 0. That means it is a balanced tree. Now you can have other types of skews such as right left, means you can see here first it was proceeding towards right and now it has started proceeding towards left. Okay, so in this case you have to perform the AVL rotation in 2 steps, that is flip rotation node. So first step you have to convert the right left node to a right node, and then you have to perform the right rotation which we just now discussed. Okay, so 2 steps. First we have to convert a right to left skew into a right skew only. So for that, first let us find out the critical node. So first compute the balancing factor. The balancing factor of node 10 is -2, 12 is 1 and 11 is 0. So of course the critical node is 10 and rotation node is 12. So here we are going to perform a rotation here. We are going to flip it. Okay, what we are going to do? We are simply going to flip 10 and 12. So if I flip, I am going to simply flip your 11 and 12 here, such that 11 is going to in the position of 12, and since 12 is greater than 11, it will be on the right side of 11. So you can see here we are doing nothing with the critical node right now. Okay, so we will do with the rotation node. So what are we doing? The rotation node and the next node we are just flipping it. So when you flip it, you can see the tree now becomes a right skewed trees, right? So that is what we wanted. So from a right left skewed tree, we are first going to convert into a right skewed tree. Now compute the balancing factor of each node. So for node 10 it is -2, for node 11 it is -1, and for node 12 it is 0. So who is the critical node? 10, and who is the rotation node? 11. Now we are going to perform the simple RR rotation, that is the right skewed notation. So where we keep the rotation node 11 fixed, and we are going to rotate in an anti-clockwise direction. So now 11 becomes our root node by balancing factor of 0. 10 is the left node 0 and 12 is the right node, that is 0. So you can see how we have converted a right left skewed tree into a balanced tree. Similarly, a tree can be a left right skewed, means earlier it was proceeding in the left order and then it is skewing towards the right. So if we get such a tree, then of course we are going to compute the balancing factor and find out the critical and rotation node, and first we are going to convert this tree into a left skewed tree. So we are going to flip, which two we are going to flip? 9 and 8, that is the rotation node and the next node. So if you flip 9 and 8, what will it become? It will become a left skewed tree, because 9 will go to the position of 8, and since 9 is greater than 9 will go to the position of 8 and 8 will go to the position of 9. So now when 9 is going to the position of 8, and since 8 is smaller than 9, it will be coming towards the left hand side. Now you compute the balancing factor of each of them, and we can find out that 10 is the critical node and 9 is the rotation node. So now we are going to simply perform the LL rotation, that is the left skewed tree rotation, that is rotate in in a clockwise direction from the rotation node. So this is what we get, and the balancing factor of each of these nodes is 0. I hope you understood all the 4 rotations of AVL trees. In case if you have any queries, you can write it in the comment section. I will be happy to solve your queries. So for more such informative videos, please don't forget to like, share and subscribe to CSE Core Concepts. Thank you.